Today we are going to examine Newton's second law for rotation. So we're going to look at how we can get an object to rotate and how that then defines how the object's rotation is going to change and leading into describing the rotation of the object. So let's first recap what Newton's second law is. Remember, Newton's second law told us that the sum of the forces acting on an object is equal to the mass times the acceleration of that object. So, if I have a net force that's non-zero, then my object is going to be accelerating in the direction of that force. That's translational acceleration, so acceleration along a direction. But what about rotation? If I know that I can cause an object to rotate and I can get that object to speed up or slow down as it rotates, then the rotational acceleration might somehow be related to what causes the object to rotate in a similar form of Newton's second law. And indeed it does. So remember, we talked about a torque. A torque got something to rotate. And we find that the net torque also examines an object's rotational state. The net torque causes an object to rotate. And if we want to examine the relationship between that rotation and the torque, we can follow an analogy to Newton's second law. So, similar to Newton's second law, where the mass was this inertial state, this resistance to change in motion, we know that a resistance to change in the rotational state is called the rotational inertia. And that depends, recall, on two things. First, the mass distribution and the axis of rotation. So there's a great video in this series on rotational inertia if you need to recap that. All right, so the getting an object to rotate certainly must be dependent on that rotational state. So if I increase the moment of inertia, if I make it more difficult to change an object's motion, then that net torque is going to need to be larger to get it to have that same change in the rotation. And of course, if we're describing an object's rotational acceleration in an analogy to Newton's second law with the linear acceleration, we would look at the rotational acceleration alpha. So, in a similar way that the net force causes a mass to change its acceleration, the net torque causes an object whose rotational inertia is defined by its mass distribution and axis to change its rotational acceleration. All right, so let's look at a practice problem to sort of utilize this idea. Imagine that you have a uniform rod of length L, and it's pivoted at one point. So it's out here horizontal like this, and it has length L, and we're again going to say it's a uniform rod, so evenly distributed. Now, if we held that rod horizontally and just simply let go of one end, we know that the rod would swing down in that direction. So, given that behavior, what is its rotational acceleration? And let's review our rotational kinematics and also look at its tangential acceleration. So what is the initial angular acceleration? And therefore, what is the initial tangential acceleration associated with that initial angular acceleration? Well, what's going to cause that object to accelerate? Well, a torque. And if I think about if it's anchored at this point, let's look at the forces acting on that object and, through an extended free body diagram, examine the torques. So we're going to draw an extended free body diagram of this object. So there it is. We know that the pin must be exerting, let's use a different color. We know the pin must be exerting a force on that object. But I don't know the direction of that force, so I'm just going to put a horizontal and a vertical direction just on there as placeholders. You might be able to intuit that one of those may not exist. What else is acting on this? Well, the force of gravity, it's a massed object. We know that the force of gravity acts at the geometric center for a uniformly distributed object. And we're told that this indeed is uniformly distributed. So here is our force of gravity. There's really no other forces acting on the object. All right. Well, we know that the moment of inertia of a rod fixed about an axis on its end is given as 1/3 the mass of the rod times the length of the rod squared. So because we're going to be looking at the angular acceleration, we certainly need to know the moment of inertia of that object. Okay, well, what is the net torque acting on this object? Well, as all of our net torque experiments, or excuse me, problem solving has been, we have to set a pivot point. So I'm going to set my pivot point here at the pin so that the force exerted by the pin is removed from the analysis. I have this radius for the force of gravity, and if I extend that radius and there's my angle, that is the angle at which the force of gravity is causing the torque. So looking at the torque, we have the torque of the force of gravity is our only torque acting on the system about that pivot point. We have the mass of the rod, m times g. The radius is 1/2 the length of the rod times the angle of negative 90 degrees. So my length of the rod is L. It's a uniformly distributed rod, so the geometric center is at 1/2 L. And we see that this angle, if the rod is purely horizontal, that angle is negative 90 degrees. All right, so that's our relationship for the net torque. So just putting this into a form that's easier to get rid of that angle, we have minus mgl over 2 as my net torque. All right, so that is our net torque. Now let's determine our acceleration. So we know that the net torque is equal to the moment of inertia, or the rotational inertia, times the angular acceleration. The net torque is minus mgl over 2, which is equal to 1/3 ml squared. It's our moment of inertia for a rod fixed about its axis times our angular acceleration. So we find then, if we do a little equation manipulation, solving for our value, we find that the angular acceleration is equal to minus 3g over 2l. So multiply both sides by 3. My m's go away, divide by L squared. I have an L in the bottom. Now, should it be negative? Well, it's rotating in the clockwise direction. It's going to be speeding up and moving in the clockwise direction, so the acceleration should be negative. All right, so using this idea of net torque, solving for the net torque that we have been doing a lot of, and then applying the idea, well, what does that cause for the acceleration? Okay, the second half of the question asks, what's the tangential acceleration at that point? Okay, well, we know from our discussion of kinematics, rotational kinematics, that the tangential acceleration is equal to the radius times the angular acceleration. So our tangential acceleration is equal to the radius L times the angular acceleration minus 3g over 2l. And we get our tangential acceleration of 3/2 g. Now, should it be negative? Well, it's starting at rest, and it's going to be moving in the downward direction right at that initial point, and therefore, motion in the negative direction, speeding up, the acceleration better be negative. Interestingly, it's larger than gravity. So that means that this end is accelerating at a faster rate than gravity. Well, that's kind of cool. So how can we test that? Is that really possible? Well, I suggest that you try this at home because it's sort of fun to do. So take a ruler, a heavy one, not a floppy one, and hold one end of it and have someone else hold the other end of it. Stick a penny on the top at the very end of that ruler. If the acceleration due to gravity is faster for the end, sorry, let me rephrase that. If the end of the ruler is accelerating more than the acceleration due to gravity, when you release the end of that ruler, the penny will accelerate at the rate of gravity, but the ruler should be accelerating faster. Does the ruler leave the penny? Does it travel accelerating faster and the penny falls down? Give that a try. You can test whether or not this is appropriate. All right, good job.